Let me read through our solutions for 5, 6, 7, and 8, and 9, excuse me. So for number 5, should get negative 1.3 repeating meters per minute. 6, I have 200 pi centimeters cubed per second. And again, if you wrote that as a decimal, like you multiplied the 200 times pi, that's fine.
What is 1.3 repeating as a fraction? Negative 4/3? Okay. That's the same thing.
Yeah, 4/3 is 1.3 repeated, yes. So again, if you wrote it as a fraction, totally fine. That's totally fine. No problem. 7 was negative 3/4 foot per second.
Did you want us to simplify that? Like if I got negative 6/8, would you still take it? Or?
Yeah. Yeah, and you would as well.
Okay.
8 would be 14 centimeters squared per second. And then stapled this too high up. I think this one is 9 is, yeah. 9 is 0.278 meters per minute.
What's the fraction do?
I don't, what's it got? It's got a pi in it, so it's,
5/18.
what's that?
5/18.
5/18. Yeah, that's probably right.
Yeah,
Sounds right.
I got it.
I didn't write that one as a decimal or as a fraction because it was too much solving going on. So yeah, I'm just gonna write this. And the calculator goes. Questions on 5 through 9 that you guys want to talk about? Yeah.
Can you notice this?
6. Sure.
This is from last semester, right?
Yes, these are last semester topics. Yep. All right. So again, my directions say you should start by drawing a picture. So there's my spherical balloon, and it says it's inflating. So I'm going to kind of like draw my picture where it, I'm showing the change happening. Oftentimes that's helpful. And it's asking about the volume increasing and the radius. So, the V and the R are the two pieces I need. If I think about my parameters, radius and volume, as that sphere is increasing, both of them are variables, right? They're both going to be changing. And because they're both variables, they're both going to generate a rate variable when I do the derivative. And let's see, record all numerical values. So I'm just have we're told the radius is increasing, so we know that value is 2 centimeters per second. And we want to know what the volume is increasing when the radius is 5. So far, so good. Because I have both, like I have the one rate variable I'm given, the other rate variable is what I'm solving for. I should be good to go. Nothing to eliminate, no parameter that needs elimination. And this is getting a little thin, probably hard to see in the back. Let me make my pen thicker. So I'm going to take find an equation that models the situation. So we're talking about the volume of a sphere. Use the volume of a sphere formula. My suspicion is this would be something that would be given to you on an AP exam if they expected you to use this. And then we'll do the derivative of both sides. And then we just need to plug in. And then just like grinding out an answer. Does that feel okay, Sammy?
Yeah.
Okay. So again, like the calculus step here is very light, right? We just do like one derivative, one implicit derivative, and then plug in some values. The hard part is getting through the setup and recognizing what's the variable, what's a constant, and like what values I plug in where, and like that r equals 5 is not a constant value for the radius, it's like a time parameter later on, so it's like at this instant. Yes, sir.
Why isn't 4/3 pi like constant when you do derivatives?
It is, I pulled it out front, right, like when I have like, you know, the derivative of 5x squared, I do like 5 times. Right? Like I did the same thing with the 4/3, I just pulled it to the front and took the derivative afterwards. Does that make sense?
Yeah,
Okay.
I just thought it'd be like 0.
Yeah, I mean, if you want to do a product rule with a constant, where you have 0 times that variable part plus the constant times the derivative part, that's fine, but like, I hate to do that. It's like kind of overkill, you know what I mean? Lucia,
You can convert the
from this, yes. I'm gonna erase this piece, because that was an aside. All right. 8 says the length L and the width W of a rectangle are changing with time. The length is increasing by 4 centimeters per second, while the width is decreasing by 1 centimeter per second. Find the rate of change of the area when L and W, or when L is 10 and W is 6. Okay? So, I don't know. So I'll draw my picture. And then like, they do that the right way. Length is, just do that. Okay. So that's kind of like what's happening to the picture, right? And we're talking about areas, so I know that each of these I'm going to care about their area. And now I'm ready to start assessing my variable. So I have like 3 parameters here, right? Now all of these should be changing, right? So they're all variable. So they're all going to generate a rate variable. And we're told that the length is increasing by 4 centimeters per second. So that's my dl dt. And the width is decreasing by 1 centimeter per second. So that's my dw dt. And then I'm looking for the area when length is 10 and width is 6. Lucy, does that feel okay so far? Okay. So I got everything I need. There's no elimination of variable needed because I know all but one of my rate variables, and the rate variable I'm missing is the one I'm looking for. Right? That's what the question's asking. So far, so good. So hopefully it's obvious that the equation to describe the situation should be length times width is area. So,
I'm sorry, why do you take the derivative of that one if you already have the derivative of the width and length with respect to time at the top?
Because I need to look at where area is changing, so I need a dA dt.
Okay.
So the only way to generate that is by doing the derivative. Does This is a product rule though, right?
Yeah.
So there's my product rule. And now I should just plug in. So length is 10 at this instant. dw dt is -1. Width is 6. And dl dt is 4. -10 plus 24 is 14 whatever's, I think, centimeters per second. Yes?
Why did you switch the dwdt and dldt? Like, wouldn't it be like ldlt? Like that's
So here's what so I'm doing a product rule here, right? Let's just include an extra step. So I have L times the derivative of W plus W times the derivative of L,
Oh,
right?
right, yeah.
So that's going to give me L dW dt plus W dL dt.
Okay.
Does that
Yeah.
feel okay? Alice?
So I got
L dl dt times W plus L dw dt times W. Like, why wouldn't, I don't understand how those things disappear, like, when you do it.
Right, okay. So if I have ddx of x, I get
X dx dt dt.
I just get 1, right? Because the parameters match, right?
Yeah.
If I have ddx of y, I get 1 dy dx, right? So the derivative of y is 1, and then the chain rule says I have that differential.
Yeah.
So that's what's happening here, right? The derivative of w with respect to time is 1, and then the chain rule gives me the dy dt,
Okay.
or dw dt. Does that?
Yeah.
Okay.
so
Good questions. Yes,
If it
go
was
ahead.
like if it was like d dx times 2y, that would just be like 2 dy dx.
So hypothetically, yes. Like if this was w squared here,
Yeah.
I would have 2w dy or dw dt.
Okay.
Does that feel okay?
Yeah.
So it's just because of the kind of the setup to the problem why everything just kind of feels like it disappears.
Yeah.
And the wrong piece are with the wrong things. But if you walk through like the product rule on it, it's like, okay.
Yeah.
Right, so like, you good? Alice good? Okay. How are these going in general, guys? Lucas?
You do 5.
5? Yeah. Sammy, was that gonna be?
No, I wasn't asking a question.
Oh, okay. Because again, we're gonna have like at some point, a little mini test on just this topic, right? In the not too distant future, probably sometime next week. So,
We have Monday off also.
we do have Monday off next week. All right, so it says water is draining from a conical tank whose radius is, I screwed this up on my paper that I printed off and I have it screwed up here. Whose radius, right? The height is decreasing at an unknown rate. The radius is decreasing at this, the volume is decreasing at that. How fast is okay. So that radius doesn't even need to be there. So here's my conical tank, right?
Oh, that's good.
And there's like some water in it. And as time progresses, the tank isn't changing, but like, the height of the water does, right? Feel good? And since we're talking about volumes here, I know I'm going to need those things, right? And notice I'm only caring about the volume of the water. right? Not the volume of the tank. Don't care. So if I look at this problem, all of these guys are variables, which means that they're all going to create a rate variable when we do the derivative. If we read this, it says the height of the water is decreasing at an unknown amount. The radius is decreasing at 1. And the volume is decreasing by 8. And we want to know how fast is that height decreasing when...
It's 8 pi.
Oh, 8 pi, thank you. Yes. When the water is 2 deep and the radius is 3, right? So what it says on your guys' sheet?
H equals 2, R equals 3.
Yeah. Is that what you guys are given also?
Yeah.
Okay. I had to update, I typed this problem out the first draft and I screwed it all up and things were missing. I had to go and retype it. And I thought I updated your guys's, but the one I'm looking at is like the unupdated one with like my own little edit marks on. I want to make sure that I gave you guys what you needed.
So the reason why the variables are in like their derivative form is because it's looking at the rate of how fast it's going on, not like how much is actually like, not like the size of
So for every variable in our that we're going to deal with, if we're going to take the derivative, we're going to create a rate variable for every variable.
Yeah.
So I also, when I list the parameters that are describing the situation, if they are variable, if they're changing with time, I need to have that information also. So this is what I'm checking to make sure that I don't, to see if I need to eliminate a variable. So if I'm just looking for one rate variable, I'm good to go. There's no elimination of variable needed because I have the volume rate, the radius rate, and I'm looking for the height rate. I can find one missing thing. That'll be fine. Everybody good? Okay. So the volume of a cone is what's going to be describing the situation. So far, so good. I'll take my derivative. Now, when I take the derivative of the right-hand side, what do I need to do? Product rule here, right? Everybody see it?
Yeah.
Okay. So I'm going to have 1/3 pi times r squared, and then the derivative of h, plus h, the derivative of r squared. Looks good. And again, you could take the 1/3 pi and put it on, attach it to each of these things if you want to. It's 6 of one, half dozen of another. Is everybody okay with the way I've written this though? Okay. So now we just fill in. So the dv dt is 8 pi. R is 3. dh dt is what we're looking for. H is 2. R is 3. And dr dt is, oops, that's negative, is -1. Now it's just some gross algebra. Lucas, does that work for you? Okay. I'll let you guys handle the algebra at the end to solve for the proverbial x there, but it's, it's algebra 1 level algebra at this point, right?
Question, for the quiz on this stuff next week, we need to know all the, chain equations, like equation for volume, equation for,
I would probably give you like the volume stuff if you know your basic areas, like area of a square, area of a circle, like a perimeter, Pythagorean theorem.
What's the area of the circle?
pi r squared. But like volume of a cylinder, volume of a sphere, volume of a cone, I would probably get those two. Yep. And when it gets closer, we can talk through the details. I haven't written it yet because I've been waiting to kind of see how this goes. Do we feel okay about this stuff? I think somebody, Lucia, was it you said you had a 5-1 homework question?
It wasn't 5-1, it was only 4-9.
Oh, it was a 4-9er. Okay. Well, let's go back to that then. Lucia, what are we looking at from 4-9?
Number 17 and number 19.
Okay.
It's just when like the secant and tangent gets involved.
Okay, sure. Okay, 19 we shouldn't have done. Did I assign 19?
Yeah,
Ugh,
321.
yeah, my bad.
Okay.
You know why?
Yeah.
That's hyperbolic cosine. We don't do any hyperbolics in this class. You're not expected to do it on the AP. Don't worry about 19.
Okay.
17 though is one that's doable for us.
Okay.
So, oops, can you, come on.
What's it?
So we'd say the antiderivative of h. What function gives me a derivative with sine in it? So negative cosine, the derivative of negative cosine is positive sine. You good with that?
Yeah.
So you have 2. We can just kind of pull that outside. Because the derivative of cosine is negative sine. So negative cosine gives us negative sine, which is positive. Right? And I'm just going to do the minus. And I'm going to think, okay, what derivative gives me secant squared? Tangent. And derivative of tangent is just secant squared.
Okay.
And then the one last thing I need is
Plus C.
plus c. And we're done.
That's it.
Done. I mean, you could simply make this -2 cosine, but like, whatever.
So you're basically just working backwards, trying to figure out like what derivative will give you. Okay.
Yes, that's exactly what you're doing. And in fact, when we did the 4.9 and we gave you this table, here's like, again, we don't need those guys, but like, you're just kind of reading through your table. Oh, I have secant squared, the antiderivative of tangent. So it's the same, these are the same as the derivative rules, they're just running in the reverse direction. Cool? Perfect. Anybody else? Brooks?
I wasn't here last week, so I don't know for sure, but is an antiderivative just the same as an integral? They're the opposite? Or...
We haven't even said that word yet.
Oh, never mind.
That I word yet. So we are going to connect those two ideas, but we haven't even said the I word yet.
Sorry.
That's okay.
I don't like the end.
No, it's good. It's good.
Oh.
Yeah, it's good.
I think that's
All right.
Are we staying today?
Yes. So last time we spent the class building out how to calculate this area under the curve, right? We said that area under the curve was the limit as n goes to infinity, the sum from I equals 1 to n of our function f of x sub I, where we define that I in a certain way. But here, we had mentioned in class that like you could use right-hand endpoints or left-hand endpoints or midpoints or really any value on that little subinterval you're investigating. What's up? She is.
Could you just have her stop by the office? Thank you.
They want you in the office at some point.
Okay.
Right, and so to say that like, yeah, this works for right-hand endpoints or left-hand endpoints or midpoints or whatever point you want to do, as long as it's between like the little interval that we're, like whatever x value you want to use to build the height on that little sub-interval for the rectangle you're building, whatever, it doesn't matter what x value you use as long as it's in that little sliver that we've chopped up. So we use xi star there. And then remember, delta x was this b minus a over n, right? We're going to give this formula a name. We're going to call it the definite integral from a to b of f of x. So this is like, kind of like a stretched out s. Why do you suppose it looks like a stretched out s?
It's supposed to represent a function.
What does this thing do? Sum, s for sum. Okay, so that's why it's a stretched out looking s. Okay, so this guy over here is our definite integral, where the dx is like our delta x, the f of x is like our f of x, like the function we're looking at, and this piece is like my integral symbol. Okay. All right. So a little bit of math history. Calculus was developed between two men independently of one another. There was the German Gottfried Leibniz and the Englishman Isaac Newton developed the principles of calculus like in parallel, independently of one another. Most of the notation that we currently use is the Leibniz notation. Newton was doing everything with like lines and slopes and geometrically, which is just like a nightmare to do any kind of like analysis by hand because it's like all graph intensive and it's like kind of a mess. Leibniz was doing everything kind of algebraically, and that's the notation that's kind of stuck. So this stretched out S symbol is the integral sign. It's like the addition sign or the subtraction sign or the multiplication sign. It's an operation. The function that we are integrating, that we're taking the integral of, is called the integrand. That's the f of x that's on the inside. The a and b are the limits of integration. That's telling us where we're going to start integrating from and where we're going to stop. The dx is just telling us that we're integrating with respect to the variable x, so it's indicating the variable of integration, just like the dx and ddx is telling us like what variable we're differentiating with respect to. Because believe it or not, you go long enough and you start, doing calculus and multivariables. So like, that's usually a Calc 3 topic. Because why would you want to do this in more than one variable?
Are we in Calc 1?
We are, this is like the bridge between like Calc 1 and Calc 2 traditionally.
How many calcs are there?
Most undergraduate, like math curriculum will go through Calc 3. Depending on how they name things, they may have a Calc 4 course, or it might be called differential equations. Depending on how the school is naming things, could also be considered another calculus course.
Like calculating.
Or you could do, and like most undergraduate math degrees will have a, advanced calculus or real analysis course that'd be considered like another calculus course, depending on like what the university, how they have things structured. BC, the BC course is basically Calc 1 and 2 as an undergrad. AB is like Calc 1.5 or 1.1, 1.1 and a third, somewhere kind of in that, half to a third. Is everybody okay? All right. So x is just a variable name, right? So whether we write the integral from a to b of f of x dx, or we write the integral from a to b of f of t dt, or the integral from a to b f of r dr, nothing is really meaningfully changed, right? The letter, the variable name doesn't really matter to us, it's just a name. It doesn't appreciably change anything. Just like if I did d dt of t squared, sort of the same problem as d dx of x squared, right? All right, a little bit of a name. So this sum of rectangles that we built out last time actually has a name. We call that a Riemann sum. Another piece of math history that's named after the mathematician Bernard Riemann. And basically the idea here is that like your definite integral, we can approximate with a Riemann sum. You know, and as n gets bigger, the accuracy of that approximation should increase, right? That's what we observed last time. I asked you we built an upper and lower bound for our area under the curve. And I asked you, we looked at some approximations, like how many rectangles do I need to get the area exactly? And right away, somebody was able to answer in both classes, like infinitely many, and it's like exactly the right idea. But you should observe that as n gets bigger, the accuracy of that approximation should increase, right? And that's something we observed last time. All right, new idea though. This is something we didn't hit last time. So let's say our function f of x takes on both negative and positive values, that part of the function is above the curve and part of the function is below the curve. It will now be possible, if we think about it this way, for the area under the curve to potentially be negative, because we're going to count the rectangles that are built below the curve to have negative area, and the rectangles above the curve to have positive area. So your area under the curve could be 0, like the negative parts could cancel out the positive parts. It could be negative, where you have more area under the curve than above the curve. Or it could be positive, where you have more area above the curve than below the curve. Is everybody okay with that? So in particular, what's going to matter to us a lot is figuring out where the function changes from positive to negative, right? Because if I'm going to calculate the area under the curve, I probably want to calculate this area, and then subtract that area. Everybody's okay with that idea? Because inherently with the way we're describing this, you know, the area doesn't need to be, isn't inherently going to be negative, right? Now, if we're using an f of x, and f of x just has a negative value down there, then I don't have to do anything, right? Because the height of my rectangle will just be a negative height, which will give me a negative area, so I'm good. Now, if we start doing absolute values and stuff, then I need to be really careful, but like, that's later. Is everybody okay? The concept of negative area I know is like, ugh, but like, you see why we're going with it, right? Okay. So, what we want to talk about now is this concept of integrable, right? So we have the corresponding concept of differentiable, right? We say a function is differentiable if the derivative exists, right? So we have differentiability at a point or differentiability over an interval. Everybody's okay? Now, integrability at a point makes no sense because we're talking about area under the curve, and if it's just one point, the area there has got to be 0, right? If you have the area under a single point, you can't, it has no length or no width, right? It just has some height. So 0 times whatever is still 0. So what we want to say about integrability is that the definite integral exists, right? So we say a function is always going to be integrable over an interval, right? We say a function is integrable from a to b if the definite integral from a to b exists. Is everybody okay with that? Now, you might say, okay, when wouldn't it exist? When can't I find an area under a curve? Like, does a discontinuity matter? Right, like, so, oh boy, that's thick. That's fine. So like, let's say we have something like this. Can I still find the area under this curve, even though there's a discontinuity in it?
Yes.
Yeah.
Yeah, right? Does that discontinuity even matter to me?
No.
No, because how much area is being occupied by that discontinuity?
No.
0. Very good. So what theorem 3 here says is that one discontinuity, no problem. 2 discontinuities, no problem. 3, 4, 5, no problem. Finitely many, no problem. Infinitely many, a problem. What's that?
What would infinitely many discontinuities look like?
A mess.
So this
Like between 2 points?
Yeah.
Infinitely many?
Yeah.
So it's just like a bunch of holes?
Well, let's think about this function. So let's say f of x is the piecewise function where f of x is equal to 1 if x is a rational number, and 0 if it's not.
Oh.
So between any 2 points, like between 0 and 1, how many jump discontinuities do we have? Infinitely many, because how many rational numbers are there between 0 and 1? Infinitely many. How many irrational numbers are there between 0 and 1? Also infinitely many. We're going to have infinitely many jump discontinuities in between it. And to be honest with you, I'm not sure that there's ever like a continuous segment between those two. Right? Is there a string of irrational numbers where there's no rational number in between them? Is there a string of rational numbers where there's never an irrational number in between them? This thing is like an example of a function that's not integrable at all, right? But the stuff that you're going to look at in this class will never look like something like this. It'll always be the familiar function types you studied in pre-calculus. And the only time where you ever have to worry about infinitely many discontinuities is if you're like integrating something from like 0 to infinity, which we will talk about way later in this semester. How to do like a improper integral is what that's called. But for now, don't worry about that kind of thing. Everybody's okay? All right. So this is an example of not integrable, but like you have to get something, a cuckoo example like this to come up with something, not anything you'd encounter in this kind of class. All right. If f is integrable from a to b, then definition 2 exists and gives the same value no matter how we choose our sample points. So to simplify this calculation, let's just use the right-hand endpoint formula that we built last class, right? If it doesn't matter how we choose those sample points, let's just use right-hand endpoints, and then we can standardize this into a formula. Yes? Okay. So this is the same thing that we had from last time. So again, we need f to be integrable, but in this class, everything you're going to encounter is going to be an integrable function. So we're finally getting into a problem. So it says express the sum from, or express the limit as n goes to infinity of the sum I equals 1 to n of xi cubed plus xi times sine xi delta x as an integral
Excuse me.
on the interval from 0 to pi.
Got it.
Okay?
Any numbers in that?
There's a 3.
Oh, okay.
Yeah.
Thank you.
You're welcome. Okay. So, well, let's do this. This needs to look like that, right? That's what I need to write at the end. Everybody's okay? If it asks us to write it as an integral, it's just asking us to write it that way. So I have the a to b. That's just the endpoints of my interval that I'm integrating over. Everybody's okay there? So now I just need my f of x. Remember, my sum is a function of xi. So what is our function of xi here? Just that. And then the delta x is just becomes the dx. And that's it. That's all we have to do.
Wait, and why does the delta x become the dx? How does that change?
So remember, the delta x is like the width of our rectangle, right?
Okay.
Dx is an infinitely narrow sliver of x, which is just like the width of our rectangle.
So delta x is always just going to be the dx.
Yes. 100%.
Okay.
Yes. And you're like, ooh, I can remember that. Because they both have the d and the x in there. So that's it. That's all you had to do.
Oh,
That's all I was asking you to do. Is that okay?
yeah.
So much in the same way that we had this relation in semester 1, this is kind of the same thing, right? Where if I recognize, oh, I need to do this limit, well, that's really just doing this, and we're going to learn how to do this with shortcuts. Much in the same way, like, doing this limit is really just doing this, and we have a bunch of shortcuts to do this, right? Is everybody okay? You see the similarity, Mark?
I remember the summing aspect of the thing. What does the limit do?
So how many rectangles did we need to get the area under the curve? Infinitely many. So that's how we're going to get infinitely many rectangles. Does that make sense? Okay. Okay. So that's that. Now, if I actually want to compute, because we haven't come up with any way of computing, this guy yet, right? All we know how to do is go from this to there. Correct? I can go from function to this, and go from this to this, but I have no idea how to go from this to limit or to area under the curve. And I don't know how to, but I should know, with a little bit of help, how to go in certain circumstances, how to go from this to area under the curve. And that's what we're going to talk about. Okay? For one day, and then we're going to abandon this in favor of shortcuts. Okay?
Oh, that's great.
So this is like when we made you find the derivative using this formula, and you're all like, oh my god, this sucks so bad. And then I was like, yeah, you can do all these in your head. Let me show you this, showing you the shortcuts. And you're like, oh my god, this is like life-changingly easier. The same thing's going to happen now. You have to appreciate what the shortcut is shortcutting out before I just show you the shortcut. It's okay? All right. So, to be able to find the area under these curves, we need some of these summation formulas. So if I'm summing up a variable, this is the formula that works out to. If I'm summing up a variable squared or variable cubed, or this is how I sum up a constant, or I can pull a constant away, or if I have the sum of two terms, I can distribute the sum across the addition or subtraction. So these are like our rules that we can use to manipulate our sums, are like these guys. And then these ones are going to be how we can do a substitution to replace our sum with something we can compute. Is everybody okay? So these are going to be my tools that I'm going to use to evaluate some of this stuff. Okay. I need some space here. So this is going to be like the stuff you would do in your homework now, right? That first example, you'll do that in the homework where you just rewrite it as an integral. Here we're going to take a function. We're going to use right endpoints from 0 to 3 and n equals 6, and we're going to calculate the Riemann sum. Everybody's okay with that? So that's adding up rectangles. I'm going to try to do this without drawing a picture. Is everybody okay with that plan? Okay. So I'm going to start by calculating my delta x. Remember that the delta x formula is b minus a over n. So that's 1/2. Everybody's okay with that? My xi is a plus I times delta x. So like x1 is going to be 0 plus 1 times 1/2, or 1/2. x2 is going to be 0 plus 2 times 1/2, which is 1. x3 is going to be 0 plus 3 times 1/2, or 1.5. x4 is going to be 0 plus 4 times 1/2, or 2. x5 is going to be 0 plus 5 times 1/2, so 2.5. And then x6 is going to be 0 plus 6 times 1/2, which is 3. Peyton.
Why do we use that like equation and not just add? Like now that it's gonna be 1 more 1/2 every single time. Like when would it not be like?
If you don't start at 0, if you're not doing the delta x is something inconvenient. But yes, that's essentially all you're doing.
Okay.
I'm just trying to like connect the formulas to what you're doing. But that's exactly what you should think in your head, right?
Okay.
Like I'm gonna, okay, first interval is 0 to 1/2. I end at the right hand side, so that's the 1/2. Next interval will be like 1/2 to 1, and you go 1. And so you're just building, you could draw it out in your head, just to say, yes. I'm just trying to connect it to the formula.
Okay.
Is everybody on board so far? Okay. So my sum from 1 to 6 of f of xi delta x is going to be, so f of 1, or well, I'll write it this way. So I'm going to have f of x1 times delta x plus f of x2 times delta x, all the way out to f of x6 times delta x. Does everybody feel okay there? Now we're told f of x is x cubed minus 6x, and I know x1 is 1/2. And I know delta x is 1/2. And then I just kind of keep on going. And then I just pound that through my calculator, right? So again, if I'm matching up just like that, right? Oops, too far. Does everybody see what I'm doing? You pound that through on the calculator. I don't care what it really is. Is everybody okay?
That's just plugging all in to find the area.
To approximate the area. Right, the actual area we're going to now find in part B.
Is it 6? Is it like 6 different like chunks like that?
Because n equals 6.
Okay.
It's asking to slice it,
Yeah.
make 6 slices. So now I'm going to use this to go backward to the limit of a Riemann sum. So far, so good. Okay. Now, what is delta x equal again? Not 1/2 now. It's going to equal 3 minus 0 over n, because n is no longer 6, right? N is abstract, it's generalized, because we're taking the limit as n goes to infinity. But you're close, right? We're using that formula.
When you write n at the top of the sigma thing, does that mean when it ends, right?
Correct.
Okay.
Is everybody okay with what I've done so far? Okay. Now I'm going to replace my xi. Oops, I just had that as blue. Okay. So remember the formula for xi. I'm going to do that. A is 0, I, and then delta x is 3 over n. Are you still doing okay?
Where do you get the plus, like, I'm confused out here. But
Yeah. So ask, okay, so this is this, because I am using this formula here. Our A is 0, and our delta x is 3 minus 0 over n. Oops. So I have A plus I times delta x. So far, so good?
That was the formula for the infinite one.
That's for right-hand Riemann sum. But we're always going to use a right hand when we're doing it this way. We could always just as easily pick a right, left hand or midpoint. It doesn't really matter, but like we're just going to pick one and go with it. Okay. So far, so good? We're all okay? Now I'm going to F. What was F again? X cubed minus 6x, right? So I'm going to go ahead and make that substitution now. Just write this as Everybody okay so far? Okay. So now I finally am getting someplace to where I can start using my summation formulas from before. The idea is I want to whittle this all the way down till it's a limit problem. You see why, hopefully at this point, why it's like, this stinks, Mr. Kulik. I hope there's a shorter way of doing it than this. There is. So first thing I'm going to notice is that this is the only stuff that depends on I, right? So I'm going to pull that 3 over n out front of the summation. And I'm going to simplify this stuff inside of here. So it's going to be 27i cubed over n cubed minus 18i over n. Now I'm going to distribute my summation across. Oops, that should be 27i cubed, excuse me. Oops. So I distributed the summations. What's up? Yeah. Yeah. And now if I look inside here, with respect to the summation, the 27 and the n cubed are constants. They don't depend on I. And in the second sum, the 18 and the n, again, are constants. They don't depend on I, so I can pull those out of the summation. We're so close, guys. Actually, we're not that close. I don't want to false advertise. You guys are going to be mad if you see, like, if I say I'm so close and we're not like that close. Now, this guy and this guy, these were on my list up here. Yeah, this keeps going. So This is I cubed I can replace with n times n plus 1 over 2 squared. And I can replace with n times n plus 1 over 2.
Those are gonna be. Do we have to memorize this?
No.
Oh,
Yeah,
no.
all of
You
it.
have to remember that.
Not all.
Oh my god.
Even if you're doing 10 of these.
Infinite amount of
Guys, please. Hang in with me till we're done. Okay?
How many times is it?
Okay. Now what I'm going to do is I'm going to distribute this guy through. And we'll be finally at a point where I can do my limit. Three times 18, that's 54, I think, right? Hold on. I know you're out, want to get out of here. We're just right at the end, though. Right at the end. If I look at this limit, I have a degree 4 polynomial over a degree 4 polynomial. So it's leading coefficient over leading coefficient. And then I have a degree 2 polynomial over a degree 2 polynomial. So that's going to be leading coefficient over leading coefficient. Oops, except that's a 4, sorry, because it's 2 squared. And then you're at your answer. I know. We'll do some more with this tomorrow.
Zoom out. You should zoom out real quick.
No, you gotta zoom a little bit.
Yeah,
You gotta zoom in to emphasize the thing.
There you go.
that's one problem.
There you go.
Wait, what method?
Jack's like,
Yeah,
this is
Jack-
really easy.
Jack did this.
Oh, you really? Oh, never mind.
Jack's like, I did this in fifth grade. We're just in that uncomfortable place where you're doing integrals
Thank you.
at the limit of a Riemann sum.
I know. I'm trying to complete.
No. Yeah.
Every day in school.
Take care.
You're doing the off way though.
Shut up. I don't.
Yeah. We're just. It's before we start the shortcuts. So.
Yeah.